240 volts GFCI breaker will not work without a neutral connection to the breaker. The neutral conductor is a critical part of the GFCI protection circuit, and without it, the GFCI cannot function properly. Ground fault circuit interrupters work by comparing the current flowing in the hot and neutral conductors. If there is a difference in current, indicating a ground fault, the GFCI will trip, interrupting the flow of electricity and protecting the person from electrical shock. The neutral conductor provides a path for the current to return to the electrical panel. Without a neutral connection, the current cannot complete the circuit, and the GFCI will not be able to detect a ground fault. Therefore, if a 240 volts GFCI breaker is used without a neutral connected, it will not be able to provide any protection against ground faults. This means that the person using the electrical equipment may be at risk of electrical shock. It is essential to connect the neutral conductor to a 240 volts GFCI breaker for it to function properly and provide protection against ground faults. Using a GFCI without a neutral connection compromises safety and does not provide adequate protection. A GFCI, or ground fault circuit interrupter, is a safety device designed to protect people from electrical shock. It does this by monitoring the current flowing in a circuit and quickly interrupting the power if it detects a ground fault. A ground fault occurs when electricity flows through an unintended path to ground, such as through a person's body. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor outlets. They are designed to trip quickly, typically within 25 milliseconds, to prevent serious injury or death. The basic principle behind a GFCI is to compare the current flowing in the hot and neutral conductors of a circuit. Under normal conditions, the current flowing in the hot conductor should be equal to the current flowing in the neutral conductor. If there is a difference in current, it indicates that some of the current is flowing through an unintended path to ground. This difference in current is known as a ground fault. When a GFCI detects a ground fault, it quickly interrupts the power to the circuit. This is done by a relay that trips the circuit breaker, cutting off the flow of electricity. The GFCI is designed to trip at a very low current level, typically around 5 mA, which is enough to cause a shock but not enough to cause serious injury or death. There are two main types of GFCIs: outlet GFCIs and circuit breaker GFCIs. Outlet GFCIs are installed in place of standard electrical outlets. They have a test and reset button on the face of the outlet. Circuit breaker GFCIs are installed in the electrical panel. They provide GFCI protection for the entire circuit. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. The GFCI must be properly grounded in order to function correctly. It is also important to test the GFCI regularly to ensure that it is working properly. To test a GFCI, press the test button. This should trip the GFCI and cut off the power to the circuit. Then press the reset button to restore power to the circuit. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. GFCIs are an important safety device that can help protect people from electrical shock. They are required by electrical codes in many areas. If you have any questions about GFCIs, consult with a qualified electrician. The electrical safety is paramount in any environment, be it residential, commercial, or industrial. Understanding the role and proper installation of safety devices like ground fault circuit interrupters is crucial for preventing electrical accidents. These devices are designed to protect individuals from the hazards of electrical shock by quickly interrupting the flow of electricity in the event of a ground fault. Ground faults occur when electricity deviates from its intended path and flows through an unintended conductor, such as a person's body. This can happen due to damaged insulation, faulty wiring, or contact with a live electrical component. The severity of an electrical shock depends on several factors, including the amount of current, the path it takes through the body, and the duration of the exposure. Even a small amount of current can cause serious injury or death. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. In a properly functioning circuit, the current flowing in the hot conductor should be equal to the current flowing in a neutral conductor. However, if a ground fault occurs, some of the current will flow through an unintended path to ground, creating an imbalance between the hot and neutral conductors. The GFCI detects this imbalance and quickly interrupts the power to the circuit, typically within 25 milliseconds. This rapid response time is crucial for preventing serious injury or death. GFCIs are designed to trip at a very low current level, typically around 5 milliamps. This is a level of current that is high enough to cause a shock but not high enough to cause serious harm if the power is interrupted quickly. By tripping at such a low current level, GFCIs can provide a significant level of protection against electrical shock. There are two main types of GFCIs: outlet GFCIs and circuit breaker GFCIs. Outlet GFCIs are installed in place of standard electrical outlets. They have a test and reset button on the face of the outlet. These buttons allow you to periodically test the GFCI to ensure that it is functioning properly and to reset it if it trips. Outlet GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor outlets. Circuit breaker GFCIs are installed in the electrical panel. They provide GFCI protection for the entire circuit. Circuit breaker GFCIs are typically used to protect circuits that serve multiple outlets or appliances. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. The GFCI must be properly grounded in order to function correctly. It is also important to test the GFCI regularly to ensure that it is working properly. To test a GFCI, press the test button. This should trip the GFCI and cut off the power to the circuit. Then press the reset button to restore power to the circuit. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. The National Electrical Code, or NEC, provides guidelines for the installation and use of GFCIs. The NEC requires GFCIs in certain locations, such as bathrooms, kitchens, and outdoor outlets. The NEC also specifies the types of circuits that must be protected by GFCIs. It is important to consult the NEC to ensure that GFCIs are installed and used properly. In addition to GFCIs, there are other safety devices that can help protect people from electrical shock. These include arc fault circuit interrupters, or RSIs, and surge protectors. RSIs are designed to protect against arc faults, which are a common cause of electrical fires. Surge protectors are designed to protect electronic equipment from voltage surges. By using a combination of safety devices, it is possible to create a safe electrical environment. Electrical safety is a shared responsibility. Everyone should be aware of the hazards of electricity and take steps to protect themselves and others from electrical shock. This includes following safe work practices, using appropriate safety equipment, and reporting any electrical hazards to the appropriate authorities. If you have any questions about electrical safety, consult with a qualified electrician. They can provide you with advice on how to make your home or workplace safer. Understanding the intricacies of ground fault circuit interrupters, especially in the context of 240-volt circuits, requires delving into the fundamental principles of electrical safety and circuit operation. As previously established, a 240 volts GFCI breaker necessitates a neutral connection to function as intended. This requirement stems from the way GFCIs detect ground faults and protect individuals from electrical shock. The core function of a GFCI is to monitor the balance of current between the hot and neutral conductors in a circuit. In a standard 120-volt circuit, this is relatively straightforward. The hot wire carries current to the load, and the neutral wire provides the return path for the current back to the source. Under normal operating conditions, the current flowing through the hot wire should be equal to the current flowing through the neutral wire. A GFCI continuously monitors this balance. If it detects a difference, even a small one, it indicates that some of the current is not returning through the neutral wire but is instead flowing through an unintended path, potentially through a person. This unintended path to ground is what constitutes a ground fault. When the GFCI detects this imbalance, it quickly trips the circuit, interrupting the flow of electricity and preventing a potentially dangerous electrical shock. In a 240-volt circuit, the situation is a bit more complex. A standard 240-volt circuit, such as one used for a water heater or a clothes dryer, typically uses two hot wires and a neutral wire. The two hot wires are 180 degrees out of phase with each other, providing the 240 volts potential difference. The neutral wire provides a return path for any 120 volt loads that may be connected between one of the hot wires and neutral. 240 volts GFCI breaker is designed to monitor the current in both hot wires and the neutral wire. It looks for any imbalance that would indicate a ground fault. The neutral connection is crucial because it provides the reference point for measuring the current balance. Without the neutral connection, the GFCI would not be able to accurately detect a ground fault. Specifically concerning a 240 volts GFCI without a neutral, the protection mechanism is compromised. The device relies on comparing the current returning to the neutral wire with the current leaving on the hot wires. If this comparison is not possible due to the absence of a neutral connection, the GFCI cannot reliably detect current leakage to ground, and therefore cannot protect against electrical shock. The risks associated with operating a 240 volts appliance or device without proper GFCI protection are significant. An undetected ground fault can lead to severe electrical shock, burns, or even electrocution. In situations where a 240 volts GFCI is required, such as near water sources or in damp locations, the absence of a functional GFCI can create a dangerous environment. It is important to note that 240 volts GFCI breaker without a neutral connection may still appear to function in some limited ways. It may still trip if there is a significant overcurrent or short circuit. However, it will not provide the critical ground fault protection that it is designed to offer. Therefore, it is essential to ensure that any 240 volts GFCI breaker is properly installed with a neutral connection to ensure that it provides the intended level of safety. In summary, a 240 volts GFCI breaker cannot work effectively without a neutral connection because the neutral wire provides the necessary reference point for detecting ground faults. Without this reference, the GFCI cannot accurately measure the current balance and will not be able to protect against electrical shock. Always ensure that GFCI breakers are properly installed with all required connections to maintain electrical safety.